and welcome to today's lesson. We are looking at a girl's best friend, that's right, some diamonds today. Okay, so our title is Giant Covalent or Giant Covalent Structures. And first question, what do these two substances have in common? Well, they are both forms of carbon or allotropes. Graphite is used in pencils because it has a layered structure and it's slippery, so it's used for a lubricant, while diamond is really, really hard. So, remember, in simple covalent molecules, we've got very strong bonds holding the atoms together because of the sharing of electrons. But the bonds between the molecules are very weak. So if we only heat them up slightly, they move apart, they turn into a gas at a low temperature. Okay, if we look at carbon, it's got 4 electrons in its outer shell. So that means it can bond with 4 other carbons, but each of them can be bonding with 4 carbons. So we can make it into this giant structure with each carbon bonded to 4 others. Okay, so what's the hardest substance on Earth? Well, diamond is the hardest naturally occurring material on Earth, although some artificial materials are stronger. It's really hard because it has what's called a 3D tetrahedral structure. So, the carbons are joined in a 3D structure known as a lattice, and each carbon atom is joined by 4 others with those strong covalent bonds. Okay, and that's what makes diamonds so very strong. Lots and lots of very strong bonds. Okay, so diamond. It is a transparent crystal, which is colourless if it's pure, and the shiny surface sparkles in the light because of the way the light reflects in it. It has a density of 3.5 grams per centimetre cubed. It is the hardest natural substance. It does not conduct electricity because it's not got any free electrons, and it's the best conductor of all solids. Its structure is a 3-dimensional tetrahedral lattice, where each atom is covalently bonded to its 4 neighbours. All the atoms are equally spaced. As I keep saying, very strong bonds so the atoms can't move. That makes the diamond very hard. All the electrons are fixed in bonds, and the electrons can't move, so the diamond cannot conduct electricity. And it has rigid 3D bonding. Vibrating atoms can conduct heat easily through the lattice very easily, so that makes it a good conductor of heat. Good conductor of heat, poor conductor of electricity. So what's diamond used for? Well, you must know that it's used for jewellery because they diffract and reflect light in different colours and it looks very pretty and sparkly. But because it's so hard, they're also used for cutting and polishing. And that's usually using industrial diamonds, ones that have been made artificially. So they can cut through stone, rock, teeth, even other diamonds. In fact, diamonds are pretty much the only thing that can cut diamonds. For cutting, diamonds are embedded into drill tips and saw teeth. For polishing, diamond dust is on rotating discs like a really, really fine sandpaper. Okay, let's have a look at a diamond structure.
Right, okay, so this is a model of some diamond. Each of the balls in it represents a carbon atom, and you should be able to see that each one of the carbon atoms is attached. So if we have a look at that red one close to the camera, it's attached to 4 different other carbon atoms, because remember there are 4 bonds that carbon can make. Okay, now remember each of those covalent bonds is really, really strong, which is what makes this a really strong substance. And we describe this as a lattice structure.
Okay, so graphite is another giant covalent molecule, and you can see that what we have here is layers of hexagons making up graphite. In graphite, each carbon is only attached to 3 other carbons, which leaves 1 free electron. In this diagram, the dotted lines represent a covalent bond to another carbon that we can't see. Each bonded electron has a delocalized electron, which means it can conduct electricity. So the properties: it's opaque, it's a dark grey flaky solid, it has a rough surface which is slightly shiny. Density 2.1 to 2.2 grams per centimetre. Feels hard, but it's flaky. It's the only conducting non-metal, and it's an excellent thermal conductor along its layers, but poor across the layers. So the flat hexagonal layers with the bonds to 3 neighbours are very strong bonds, but the gaps between layers are weak bonds. the layers are 2.5 times further apart than the atoms within a layer. So strong bonds make the layers hard and rigid, but there aren't covalent bonds between layers, so they rub off easily. Those free electrons mean that electrical current can flow. The rigid bonds conduct heat well. The bonds between layers do not conduct heat well. Okay, so uses of graphite. You'll know it as pencil lead, which is graphite mixed with clay. Electrodes for scientific experiments for electrolysis are often made of graphite because it's a good conductor of electricity. We also use graphite for other conduction purposes and as a lubricant because of its slipperiness.
Okay, this model represents graphite, and if I turn it slightly, you can see very clearly that it's made up of layers, and each of those layers is comprised of hexagons. And so each carbon in this is only attached to 3 other carbons, which makes it a weaker structure in the first place. And then because we've got these weak bonds between the layers compared to the strong covalent bonds within the layers, that means that those layers can slip past each other really, really easily. And where you see that and where it's useful is in one of these. So a pencil, if I just draw on my dining table, what I'm doing is I'm taking the layers of graphite off the end of the pencil and laying them onto the table.
Okay, so that showed us some of the properties of graphite, and I hope that made sense. Good luck with doing the questions that I've sent you on Fronter, and do message me if you have any problems.